Thanks for joining us for this TCU WMODAG webinar event. Glad that we have the participation that we do. This is going to be our first try at this, so apologies if there's some technical issues, but I think we've got them all worked out, knock on wood. So today we are going to be talking about the WPLMN lab results study. Just to go over the agenda for today's talk, we're going to do a welcome and an introduction. Pat will do his presentation, and then following that will be a Q&A. If you'd like to ask Pat questions throughout the talk, we're going to be using the chat area. So feel free to type in your questions as he talks, and then at the end of his presentation, we'll go through the chat and ask him the questions that are there. If you are familiar with Microsoft Teams, there should be a ribbon on your screen. If you click on this little chat bubble, that will bring up the chat function or the chat area in the lower right-hand corner. And so it will look like this. And feel free to type in messages. These will be for everyone to see, so make sure that it's appropriate. At the end of, like I said, at the end of Pat's presentation, we'll go through the chat to ask your questions and to hear his answers. Let me introduce you to Pat Baskfield. For those of you who don't know him, he is a pollution control agency hydrologist. He's worked for the agency for 24 years, and the last 12 years he's been the monitoring coordinator of the Watershed Pollution Load Monitoring Network. It's a statewide river monitoring network that has 199 sites, and they work with state, federal agencies. They work with us at the council, state universities, and local partners to collect data on water quality and flow in Minnesota to calculate loads on the rivers and streams. As part of that program, in 2014 and 2016, they had 8 different laboratories participate in a round-robin study to look at different parameters and to see what the results were and the variability of those results between those different labs. Pat, I'm going to go ahead and close my screen, and if you want to go ahead and pull yours up, you can have your presentation ready to share.
Okay.
And thank you very much for joining us.
Can you hear me and see my presentation?
Yes.
Yes.
Okay, great. And I should have looked a little closer at that intro. That was kind of outdated. It's at 2014 and 2016 we did this, and actually we started this in 2014, and we collect samples every year, so forgive me. So okay, I've got well, tell you what, let me check. Sarah Yost, are you out there?
I'm here.
All right, good. This presentation today, it's myself, Patrick Baskfield, Sarah Yost. She works for the Environmental Data Quality Unit at MPCA, and Andy Butzer, who can't be here. Andy's from our Detroit Lakes office, and it was Andy and I that kind of started this study. And Andy had a real strong, before he came to the PCA, real strong lab background at Department of Ag, and so Andy was really instrumental in kind of you know, we talked about the design and everything, but as far as pulling stuff apart, and you know, I'm not a lab guy, and Andy is, and he was able to you know, kind of tell me the dynamics on what's going on, or throw out some plausible, if we saw goofy results. You know, Andy was good at digging up plausible explanations for why we were seeing the results that we did. But anyways, like Jennifer said, I work for the Watershed Pollutant Load Monitoring Network at MPCA, and this was just a little side study that we set up, and you know, we monitor 200 river monitoring sites, and we have the GS and the DNR collect flow measurements, and our guys, or those we contract with, go out and collect anywhere from 20 to 35 samples per site. And so we've got probably 6,000 rounds of analysis every year that we send off to labs, or 6,000 samples we send to labs for analysis. And you know, so we want to make sure, or we wanted to make sure the results that we got were comparable regardless of the lab that we used. And we had We started this program in 2007, and we had some tip-offs early on that things weren't, as smooth as we thought they would be between the labs. I mean, the labs by and large are very good, and but I kind of came into this world, assuming when I first started working at MPCA that lab results were solid across the board. But lab people are people, and they make mistakes, and so anyways, I just it's something that you shouldn't oversee, just assuming that your lab results are correct. We've got some pretty solid protocols, and when samples come in from the labs, we check them, and then when we compute pollutant loads, we've got a pretty good package where we can do a lot of graphing, and just in the process of that, if something sticks out, it's usually pretty evident to us. But anyways, this analytical proficiency study, what that is, round robin basically for short, it's a study where we went, every year we go out and we pick a river and we try and say, okay, do we want clean water or dirty water this year? And we'll kind of time our sampling to that, and we'll go out and we'll grab a big sample and split it and send it to labs. And I'll go through the slides that talk about study design and results, and a little bit more on the background here, but oops. Froze. Are you guys still there?
Yes, we are.
Oh, good. It's my computer. There we go. Good. Okay, so why did we do this? This actually this data preceded the round robin. We started that in 2013, but this was the impetus for this. This is a well-known lab throughout the state, and we're fortunate enough that we've got a handful of sites where we collect samples, or what we'll do is we'll collect replicate samples, back-to-back samples, or depending on the sampler, you can also collect 2 samples and split them between bottles. But we've got a couple of sites where we collect samples for other programs as well, and they analyze some of the same parameters that we do. And so we've got comparative data sets, between our primary lab and this other lab that the partners that we're collecting samples for will send their sample to, and anyways, we get multiple samples every year that are collected at the same time and analyzed at different labs, and this was one data set that we saw. What we've got here, it's a pretty simple graph. These are basically total phosphorus concentrations from Lab C and Lab D, and in the study, next slide, I give you a list of the labs that are in the study, but I'm going to be talking anonymously. We don't identify any labs in the study, and that was part of the reason to get everybody to cooperate with us, or one of the reasons that they did. So, but anyways, we were comparing samples, 2011, Lab C and D, very comparable results, very much what you'd expect. Sometimes Lab C is higher, sometimes Lab D is higher, but the results are very comparable and flip-flop back and forth. And all of a sudden, 12 and 13, we saw the wheels fall off the bus, so to speak, and all of a sudden, Lab D is anywhere from 10 to 25% lower in TP concentrations than Lab D. And what happened in this particular case was the lab bought a new piece of equipment in 2012, and they calibrated it, and everything, was going according to manufacturer specs. But then we started seeing results, and we saw that things weren't working right, and we contacted the lab, and they dug in and recalibrated. In 2013 went by, and the same thing happened. And finally, in 2014, this particular lab said, screw this, and they got rid of the old piece of equipment and went back to the original analysis they were doing in 2011. But anyways, that was enough where we ended up throwing 2 years worth of total phosphorus data out for many, many sites, and that was a huge mistake. And we thought, we got to keep this from happening in the future. And so what we did was we thought, let's design the study. We'll contact all the labs, and in our case, we're limited to 9 labs that we use. We've got Department of Health in St. Paul, Department of Ag right next door in St. Paul, MVTL down in the southwest part of the state, they're in New Ulm. Our RMB is up in the northwest corner of the state. Natural Resource Research Institute, that's UMD's lab out of Duluth. Then we have PACE in Virginia, Minnesota, and PACE in Minneapolis, Minnesota, Met Council in the cities, and AWR up in the Brainerd region. But anyways, we contacted these labs. We told them what we wanted to do, and they were all for it. And so, whoops. um, Anyways, we contacted the labs. They were game, and we told them what we were going to do, and we collected some information from the labs, the different methods that they were using. There's different analytical methods for all these different parameters, and out of 9 labs for TP, for example, we had 4 different methods, and the procedures. We've got a list of procedures underneath here, and if you take the rows across, you can see that they're not all the same. And so we've got labs that are different methods that we're supposed to be able to compare our data, but they're doing things slightly different, and we didn't know if the results were because of procedural differences between the methods or something going wrong in the lab. But anyways, we collected this information from the start, and then the plan was we go out and we collect samples. And on top of the ledge here on the bridge, you can see a Van Dorn sampler. And what we do is we basically drop that multiple times, and we fill up this big jug next to the wagon. And if you look at the picture on the left-hand side, you can see we've got a screen on top of that jug, and that's just to grab coarse particles, be they sand or sticks or whatever. But we didn't want those in, so we don't really care about accuracy. We care about accuracy when we split. But we don't care if we knock some big particles out of this. We want a uniform split is really what we want, not to know exactly what the concentration is in the river at the time. So anyways, we screen it. We bring the sample back to the lab. This is a Decaport cone splitter. It's a 10 sample splitter. And Andy was the engineer behind this, but he made a table and mounted that. We've got a little... we fill 2 different bottles. We fill a general bottle for each lab, and a nutrient bottle for each lab. These are the nutrient bottles. They're small. They get acidified, and then we have bigger bottles that we put underneath there, so we pull the blocks out. But this thing is really a great little sampler. We've tested it, and there's specs. Every sample should be within 10% of each other, and they are. We always test that. There's a little bit of variability. These are the 2-liter general bottles here. And you can see there's a little bit of variability between the bottles, but by and large, the sampler does a great job splitting samples. The first time we used this, Andy split samples, and he sent all 10 of them to the same lab. And our procedures call for, the labs, when they get their sample, they do 3 runs on every parameter, give us the average of those runs. And that's what this lab did. They did 3 analyses for each of the 10 bottles, and everything was within 1 or 2% of each other. So we know that it splits pretty accurately. It's a very good sampler. And then we send the labs off to we send the samples off to labs for analysis. They send the results to us, to Sarah, and she compiles those results, and then we go over them. And so that's procedures and just a little bit of overview and background on the study. And now I'm going to get into the results. And we've done this 2014 through 2019, and we've got a lot of results. This table was the best way that I could figure out to describe our results. And if you look at the first column, we've got the year. Second column, we've got river and turbidity. So for example, 2014, and we sampled from the Maple River, and the turbidity was high, and that's just a relative designation I gave these samples. So we've got samples that range basically from clean water to very dirty water as far as sediment goes. And I've got the TSS concentrations below. Andy and I, we were very ambitious. Andy retires Monday. I retire in a couple of months, hopefully. If, things don't get too bad here. I'm going to wait and see what happens here. But anyways, we were very ambitious, and we noticed, over the course of time that if we ever had problems with samples, it was usually when TSS concentrations were high. And what happens is you get interference from, for example, we see interference a lot of times with high TSS concentrations affecting other results. And so anyways, we started out collecting a lot of samples that were pretty high in TSS. And then as time went on, we got lazier and closer to retirement, and we wouldn't even get out until October, and we couldn't even find dirty water by then. So, so we went to some cleaner water and moderate water, but, we wanted kind of a full range of sample concentrations. So anyways, the first year, if we move over to the next column, we've got performance standards. We only did those in 2014. And then we've got TSS, TP, and all the other analytes, and I'll go through the results. But the first one I'll go over is the performance standards. Performance standards, for those of you that don't know what they are, it's one parameter in solution, basically, of a known concentration. So we contacted a lab that makes these, and we said, we want some TP performance standards to see how accurate the labs are, and we want 5 micrograms a liter and 100 micrograms a liter and 1,000 micrograms a liter, and they sent us the bottles. And by and large, the labs did really well with performance standards, and they typically do. Real clean samples or samples without a lot of stuff in them, the labs generally do very well. And this was, like I said, we had multiple performance standards. These are the results from kind of the low level we had. And this one, you can throw out Lab B and Lab G. You can throw those out. These are basically the reporting limits. They kind of goofed up, didn't get the memo. We specify reporting limits for our program, and a reporting limit is basically the lowest level that a lab can report with accuracy. And what these 2 labs did was they ran their high-level phosphorus tests and gave us those results. And so we ended up throwing those out. But the take-home message is, the performance standards, everybody did pretty well. We'll take a look at TSS next. Now you'll see that I've got pass and I've got fail for the different years. And our criteria, when we get the results back from the lab, a lab passes if their results, their average results, are within 15% of the mean concentration for that particular year. And 15 through 19, the labs are great with TSS. 2014, that was pretty scary. So the criteria, well, shoot, I didn't finish my criteria. We have 2 things that we look at. We look at 2 standard deviations. We want all the labs, excuse me, within 2 standard deviations of the mean, and plus or minus 15% of the mean. And the standard deviations I take with a grain of salt, and this is a classic example because all of these labs pass the 2 standard deviation criteria, but that's because the results are so crappy. We've got results that go between 138 milligrams a liter and 296 milligrams a liter for TSS, which is huge. We've got over a 2-fold difference from the lowest reporting lab to the highest reporting lab. And on my job, I'd hit the floor when I saw this. I thought, oh my God, the results we've been collecting for the last 20 years, is there this much variability? And so we jumped on that right away. And one other thing I should point out here, if you take a look at this table on the right-hand side, really the only thing you want to look at, we've got the lab names in the first column. But the last column, I've got the percent deviation from the mean. So all the red boxes mean they failed, and the green boxes mean they were under that 15%, plus or minus 15% error. So you can see 2014, we had because of the huge range, everybody failed this one. We had a lot of labs that were kind of right in the 150 range, but then 3 that were huge outliers. So Andy and I thought, well, we got to do something about this. We got to figure out what the heck's going on here. And boy, my computer keeps locking up on me here. And so what we did was we got together and we said, okay, let's design a little study within a study here, and that's what we did. And the first thing we did was we identified areas of potential variability in TSS analysis. Like I said, we've got multiple methods, and they don't all do the same thing. So we got a list of the methods, and then we took a look at the procedures within those methods, how this lab is mixing their sample, what sample volume they're using, the type of filter, the pore size in the filters, they can vary, and the TSS rinse method. There's another thing called ashing, which it's heating filters up, and I'm not sure exactly what it does, but there were some discrepancies there where one of the labs was ashing a filter, and they thought they shrunk, the membranes down or the pore size down a little bit, and that could have accounted for the higher concentrations that they had. But anyways, we made a list of the potential sources of variability, and we saw that there was quite a bit between labs. All the methods weren't the same. So what we did was we developed this prescriptive method of TSS analysis that all labs were to follow. So we said, okay, here's how you mix a sample, here's the volume to use. We set them all the same filters with the same pore size, prescribed the rinse method, and what we wanted these labs to do was to analyze the next round of samples with this prescriptive method, but also to analyze these samples with their in-house method. And our assumption was that, we've got some of these procedural differences that are accounting for the discrepancies that we saw in the 2014 analysis. And so what we wanted to do was compare two things, compare the differences between labs, but also compare the prescriptive method to the results from, the in-house methods that these labs had. And these were the results that we got. And again, my jaw just about hit the floor, because sometimes I think just getting people's attention is good enough, and that seems to be the case with the lab here, or the labs here. What happened was we collected, in 2015, we collected 2 samples. We collected, and these were both dirty samples. We collected one from the Red River, and we collected one from the Le Sueur River. And so the Red River, first thing I want you to look at on the top, Red River sample mean TSS equals 348 milligrams per liter for both. So these, for both methods, in-house and the prescriptive, we got the same average, so, which doesn't mean that, both methods are giving us the same type of results, because you could have a lot of spread in one and not much spread in the other and still come up with the same mean. But that wasn't the case here. If you take a look at the graph on the left, the top one, the in-house method, we're within 2 standard deviations. But then if you look at the table over on the right-hand side and look at the percent deviation of the mean, the greatest deviation from the mean we had was only 2.4%. So these labs were all, for this method, they were fabulous. They were spot on. But then, if we go to the bottom one and take a look at the prescriptive method, the results were even better. The greatest variability we had from the mean was 1.9%, which is absolutely incredible. I mean, that was just absolutely spot on. So, because we had, basically, you look at the range for both of these, and, we're 340 to 353, 13 milligrams a liter, and about the same here. So I mean, basically, this is telling us the in-house and the prescriptive method are giving us the same results. And then within the labs, I mean, they're spot on. They did just a fabulous job. So then we go to the Le Sueur sample, and this, if you go up to the title, we've got in-house versus prescriptive TSS results. And the mean in-house, so the labs method, the mean for all the labs was 1,464 milligrams a liter of TSS. And the mean prescriptives was 1455. So again, they're giving us basically the same results. And for both of those results, the labs were within 11% of the mean. So everybody passed. I didn't put those graphs in. But what I did with this table, or with this graph down below, was I compared the prescriptive to the in-house to see how much variability we had, within the particular labs. So kind of intra-lab variability. And this shows us that basically we're measuring the same thing. I mean, there's no trends, and all these results are within 9% of each other. So that was our big TSS success. So in 2015, participating labs analyzed each so basically, I forgot a bullet. 2014, everybody failed miserably. 2015, we had the labs basically analyze their samples with the in-house method and a prescriptive method to look for the discrepancies in TSS from 2014. So the intra-lab results, or the results within the lab itself, no statistical difference between standard in-house and prescriptive results for all labs. And I should mention that you know, the labs, when they do their three subsamples for each parameter, we also look at basically the variability within those results, and they're always really tight. They always have been. And the interlab results, no statistical difference in TSS results was observed between labs. So TSS, rest assured, labs gave you a pretty good shake on that one. Total phosphorus, this is kind of a mixed bag here. We start out with concerns, so we had, you know, one lab fail out of the group in each in 2014 and 2015 Red River sample. LeSueur River sample, that was a little bit messy for TP. In fact, that was very messy. And then we had concern and a couple of passes the rest of the year. So we had basically, the point I want to make here is for TP, the labs generally do a very good job. We need to look more at these high TSS concentrations because we do see some variability. And this is what we see. So this is 2014. And let me go back. Okay, 2014 and 15 were concerns. And what we had here was we had everybody's within, well, I guess lab H, just outside of 2 standard deviations and 21% over the mean. So, you know, so that's a concern. And what we do when we see something like this, what we'll do is we won't come up with any investigation. We'll watch it for another year, and we'll try and pick out patterns. If we see a pattern, then we address it with the lab. And here, you know, so right now, just remember, okay, lab H 2014 was high. Let's take a look at 2015. And again, we have a concern, but now it's not lab H. They're down. They're not the highest, or I guess they are the highest. So they, you know, still we'll keep an eye on those guys. But they're within 15% of the mean. Oops, doggone it. Sorry, I'm on my laptop, and if I touch parts of the screen, it's or parts of the laptop, it will change slides. But anyways, we shifted. Lab D now is low, so lab D outside of 15%, and lab H is typically a little high. So let's go to the next year. So lab D was the lowest, and they are again. Lab H, they were the highest. Well, now lab A has that, I guess that title of being the highest lab. But if we take a look at the results, these are crappy. Again, this is that sample that had the 1,400 milligram a liter TSS, so this was a very dirty sample. But we see lab D, they had a low of 0.78 milligrams a liter. You know, again, over a twofold difference between the lowest and the highest, and that's not acceptable. So, you know, we had labs as much as 63% over the mean, but and you know, 3 other labs that were 19 to 33%. So this concerned me a lot, and it still does somewhat. You know, that's kind of you know, what we saw for, you know, the rest of the time period was we saw stuff like this where, you know, that the patterns, we had D, H, and A high. Well, all of a sudden now we've got G into the mix, and G is low, they're over 23%. And lab A used to be high, now they're low in this sample. The Watershed River TP sample, these were both collected in 2016, both sets of data here. So what we're seeing now is, and then 2017, life is good. And 2018, life is good. Oh, this is kind of cool. A little sidebar here. In 2018, Andy, I forget what college. One of the colleges up in the Moorhead area. I don't know if it was Moorhead State or North Dakota State, but he had a particle size analysis done on these samples, and the picture on the right is a sediment. Electron microscope picture of the sediment and all the little sediment particles stuck together. But I found this kind of interesting, you know, just to break down. We've got oxygen, silicate, aluminum. but then gold in the mix, and this was from the Cedar sample. So I figure when I retire, I'm going to mine gold from the Cedar River. Make a fortune, no doubt. And TP, again, things, well, I guess 2015 we're at a concern again, where we had one lab barely out of 15% mean, and one lab that was 20% out. So I mean, this is not horrible. I'm concerned about lab H or lab I. We added a lab. Hold on a second here. I got to figure out what year. I think it was 2015. We added another lab, so we got I into the mix. But H used to be the high one, and now I is high. So the take-home message of this is there's definitely we had some early problems, you know, with different equipment, and we had that fixed. And 2000 and that stuff was resolved by 2016. And you know, and we did have that one bad 2015 sample in Le Sueur where the numbers were all over the board. But basically, on average, for most samples, the labs do pretty well with TP. You know, we seem to have, you know, random, you know, errors every year. A different lab, you know, is kind of out of the group. But that we weren't able to pattern anything there. But the one thing that we do need to go, or those that continue this work, is the high sediment concentration analyses. DOP, that's another interesting one. DOP, that stands for dissolved orthophosphorus, and we had some pretty wild orthophosphate lessons that we learned. When we started the study, we just told labs, yeah, we want total phosphorus and orthophosphorus. And I didn't know much about lab stuff, and I didn't know there was different fractions of orthophosphorus. And so anyways, we started, you know, putting this data together, and again, we noticed something, you know, similar to what I showed you in the earlier slide, but or what the second slide down, but in that slide, 2011 was fine, and all of a sudden 12 and 13 went off, and this is a different data sets, and what happened here, this particular lab, we'd split samples and we'd get them back, and we'd be doing loads, and we'd end up throwing out all their TP or DOP data, dissolved orthophosphate, or other orthophosphate data, because it was lower than the lab we used and every other lab we compared it with. And we would contact these people and say, you know, you guys are low. And they'd say, no, we just ran tests and everything's fine. And we went back and forth for years on this, and we finally found out what happened. And, you know, and then we had years where we'd see differences, and then we'd have another year like 2013 where all of a sudden everything's back on, and then they'd go off again and then back on. And we finally figured out the mystery on this one. And these were samples that we collected for another agency, and they would send them to their lab. But what they did was sometimes they froze the samples, and other years they didn't freeze the samples. They just sent them to the lab, and then they'd freeze them again. And what happens with orthophosphate, if you freeze a sample, any dissolved minerals in there, this lab, they ended up doing a study, and they found out that when you freeze a sample, you precipitate out calcium and magnesium. They saw their total, or basically any dissolved minerals, and they saw that their total dissolved solids, you know, after they froze and thawed and retested, they saw their total dissolved solids went down. And what happened was they would precipitate that stuff out, and then the orthophosphate would form an apatite phosphorus or phosphate with the calcium that was precipitated out. And so that's why they were low, you know, because basically they were taking DOP, dissolved orthophosphate, and turning it into a form of total phosphate, a sediment-bound phosphate. So anyways, lesson number 1, don't freeze your samples. Lesson number 2, like I said, you know, we had labs when we first started this study. We said, give us your OP, give us OP results. And so we started, you know, comparing the stuff, and we would see differences, you know, kind of not as consistent as the last slide I showed you, but we saw that things were not right between dissolved orthophosphate and total orthophosphate. And, you know, so I started, you know, I pulled Andy in, and I said, what's the difference? And he said, well, total orthophosphate is not filtered. He said, but if there's a lot of sediment in total orthophosphate and they do the analysis, it's really thin lines that they run the stuff through and it'll plug up the equipment. And so I contacted the labs and I said, well, what do you guys do with your total orthophosphate when it's really sediment bound? And the labs, some labs would say, well, we just run it anyways. And some labs would say, well, it's when it's beyond a certain turbidity level, we filter it. And I said, well, what is that turbidity level? And they couldn't give me an answer. And so with total orthophosphate, it was in some labs they would just let the sample sit and the sediment settle out, and then they would draw an aliquot from the top. But what we found was with total orthophosphate, the procedures were all over the board, and we also saw interference issues, and this is what we saw. We ended up basically dropping total orthophosphate, and we went to dissolved orthophosphate, and this is what we saw when we switched from DOP or TOP. So this lab, 2009 through 2012, or actually the beginning of 2013, they had total orthophosphate as their analysis, and then we went to dissolved orthophosphate, which was 14 on, and you can see that there's quite a difference in numbers, and and that raises the question: well, does TOP measure something different than dissolved orthophosphate? And when you filter a sample, basically what you're doing is you're filtering out the sediment and any organic particles, and I'm not sure if it captures any of the dissolved organics. I don't think it does. I think the filters are open enough where that goes through. But what you're letting through is dissolved organics and orthophosphate in solution, and total orthophosphate is basically the same thing, but there may be some loosely bound orthophosphate on sediment or organic particles that will come loose, but it's not with total phosphorus. You do this rigorous acid digestion and heat, and basically you break everything down, and all phosphorus that's stuck to sediment or inorganic material or dissolved, that's all liberated, and you're basically measuring all the phosphorus in the sample. Total orthophosphate doesn't do that digestion part of it. So it's basically the same test as dissolved orthophosphate, but one is filtered and one's not. And here's what happened here. It's not measuring the same thing. We've got total orthophosphate concentrations of over 1.2 milligrams a liter. And that's way more than the dissolved orthophosphates, which that's what these are, and there's also interference with TSS, and this is how we figured that out. Is we looked at the days where these TOP numbers were very high, and these also corresponded to days with very high TSS concentrations, generally over 1,000 milligrams a liter. And this is in the Maggie River up by Duluth. And this is really a dirty river. It's very unique for rivers of the state. And excuse me, this is what we found out. Real common test to see how much orthophosphate, which is that orthophosphate is directly available for biological uptake. So plants can take orthophosphate up directly, and I guess one statistic that's often looked at is the percent orthophosphate to total phosphate, to see how much is of the total phosphate is directly available for biological uptake. And total orthophosphate cannot exceed total phosphate. It's a part of total phosphate or total phosphorus. But yet what we saw here was total phosphate it exceeded total phosphorus numbers, which is impossible. So right here, this was our indicator that we're getting interference from the sediment. And then once we pull that sediment out, generally the dissolved fraction of total phosphorus is like 1 to 2%, maybe 7%. And sorry, I know that was a lot of explanation, but that's pretty important. There's a lot of DOP problems, and so once and DOP we didn't start analyzing this one in the round robin until 2016, and what we saw, labs generally did pretty well. well, I should go back. 2014, all labs analyzed with dissolved orthophosphate. So we got that problem squared away. So the results in the round robin, everything here is dissolved orthophosphate. But we did see that in 2016, E was the lowest, F was the highest, and they both exceeded our 15% criteria. Um, F F was slightly over the two standard deviations as well, and we see the same pattern in the second sample, the Rum River sample. We do see that again, E is low and F is high, and we'll keep an eye on that, and we'll see if that pattern holds. So let's look at the rest of the year, or the rest of the years. We've got 2 passes and a fail. And so we've got a pass. So remember, E was low, F was high. E is second lowest, and F is the highest. So that pattern's still kind of holding here, but they're all within 15% of the mean. So that's that's okay. And E used to be the lowest. This one they're the highest. F is now second highest, but within 15% of the mean. And then all of a sudden now we've got B and C, and E and F are good. So basically what we've got here is, first of all, know your fractions on orthophosphate. And also, while there certainly appears to be some analytical issues with DOP, there doesn't appear to be lab-specific issues. Our fails were kind of bouncing around from lab to lab, and it's hard to pinpoint any consistent problems that existed between the labs. Nitrate plus nitrite, this is a pretty easy one. The labs, by and large, really do a good job with nitrate plus nitrite. We collect a lot of duplicates, a lot of splits, and very seldom do we have much of a difference at all with the duplicates that we collect. And so I'm not going to show you the ones that passed. Everything is great. And for 2017, with the concern I had, we had one sample, Lab B. That was quite a bit different than the other labs, but not horrible. And then in 2018, the Cedar River, this actually passed our criteria. Everything is within 2 standard deviations, but yet when I look at just the concentration range, we go from 7.7 to 9.83 milligrams a liter, and to me, that's a huge range for something that these labs should be pretty much spot on. I mean, everything that we've looked at for multiple years is spot on. So there's nothing I'm going to do about this, but I threw it in the concern category. And let's see, so nitrate results, labs generally have done well. One lab is using a different method than the others, and that was outside of the 15% threshold in 2017. So that little tidbit. TKN, this is kind of an interesting one as well. TKN, what TKN measures is it measures the dissolved nitrogen in the water, and nitrogen tied up in organic matter, and ammonia. So that's what Keldol nitrogen measures. To get that, it's a very rigorous digestion, heat, acid, liberates all that stuff, and then they measure. And these methods are not comparable. That's kind of the one thing that we found out with TKN is these methods amongst labs. Some are more rigorous than others. And so for the Watt one, we see that especially Lab E, it's way outside, 58% above everybody else outside of the 2 standard deviations. And we've got a couple of other labs that are outside of the mean, but that's because Lab E is really kind of screwing things up. And Lab E, if we take a look at the Rum River sample, Lab E is okay. But this was a real low TSS sample, so there's not a lot of sediment in this one. So what this TKN is liberating for lab F here is, for these samples, is the dissolved and the ammonia, and I guess the sample, we're just not getting the interference or the rigorous digestion that we get with here with the other lab. Sorry, I'm locked up again. Okay, so 2017, remember E was high. 2017, we see the same thing. Outside of 2 standard deviations, way outside of the 15% boundary. And that pattern holds. We get an occasional oddball, A for the Cedar River top graph here, 0.56 milligrams a liter. That would be outside the 15% mean, certainly. And and I'm just going to kind of cut to the chase on this one. E, you can see, is consistently higher than everybody else, and basically we've got a lot of inter-lab variability in TKN results. Lab E, they use a method that's different than everybody else. I believe it's SM40 standard methods 4500, but it's a very, very rigorous digestion method, and basically what they're doing is they're liberating a little more nitrogen with their Keldol method than the other labs are. So we're at kind of a quandary with what to do about that one. I mean, they're all legit methods, but clearly we're seeing some differences. So overall conclusions, intra-lab, so when they do the replicates within the lab, they're very good. So the labs, their precision is good. Total suspended solids and nitrate plus nitrite nitrogen provide the most consistent results between the labs. You can rest assured that those results are pretty good. And TP wasn't too bad. We had some random errors. It seemed every round we had one lab that fell off from the rest. But the one thing that we do need to do with this study is grab another dirty sample this year, something 1,000 milligrams a liter, or certainly above 500, and see what happens with TP. That jury's still out in my book. Orthophosphate, know your fractions, and there is some variability between the labs with orthophosphate, but it's kind of like phosphorus, where it jumps around, and a lab falls off one year and they're back on the next, and another lab falls off, and that just seems to be kind of a recurring cycle. TKN, the difference in methods accounts for the variability that we see. And labs make mistakes too. Just because a lab is certified for certain parameters doesn't mean that you're guaranteed solid results. So check your data as, and this is just me talking, as it comes in. That's so important. Make sure that the data is within the realm of what you usually see, and just kind of we just, it's more of a feel after you look at enough numbers. You kind of know what's good and what's bad, but make sure you review those results as they come in, because the lab will hold a sample for 30 days. If you do see something that looks fishy, and especially early in the year when you get these high concentrations, make sure you have the lab rerun the sample just to make sure the numbers are legit. So that's about it. That's all I have, and I can hand this back over to you. So any questions on anything, or what do you want me to do here, Jennifer?
I'm not sure where Jen disappeared to, so does anyone have any questions they want to add in the chat? Otherwise, I have one I can start with.
Okay.
if you've noticed that a lab has some pretty significant variability, are you letting them know about specific issues they have?
Yes, we are definitely. You know, like well, and yeah, I forgot to mention that. What we do is if you know if we've got kind of a concern, a warning, you know, yellow flag basically. What we do is, you know, the labs get all the results, and we identify which lab is theirs, and they compare the results with the others. But we do ask them if, you know, if things are way out of line, you know, do an internal audit, take a look at the sample, and see, you know, what happened. If it's something where there's multiple labs involved, then we'll get together with the labs, and you know, and we'll discuss what could have been the potential source of variability, and then, you know, do something like we did with TSS. We were kind of poised to do that with phosphorus, or with total phosphorus, but then, you know, we were never able to do it. So yes, that's we definitely contact the labs.
Can you guys hear me now?
Yes.
Okay, sorry about that. My mic died out. There's a question here. Your recommendation about not freezing ortho P samples, but sometimes we just have to due to time and other factors. In such cases, the sample can be passed through a 0.45 micron membrane filter using a vacuum pump and then freeze. They've then run it colorimetrically on the spectrophotometer. So I guess, what is your thoughts on if it has to be frozen?
You're going to be 10 to 20% low. The agency that did this, they were collecting, you know, in fact, for 10 years, they did that at a site, and then just discovered this. And so they're trying to figure out how they can maybe correct their orthophosphate numbers. But a lot of the samples that they had, they were tile water samples, so there was no sediment in them. And it's the dissolved solids that precipitate out the calcium, which would go right through this. Well, I guess that would depend. If I'm not sure what size filter would take calcium and magnesium out. So I guess if, and you know, Sarah, maybe you know this, but yeah, if you can get rid of the dissolved solids, then or most of the dissolved minerals, you should be okay, I think. But I sure wouldn't do it unless I tested it.
I agree. A lot of times samples might not be getting warm enough to dissolve all those minerals back in. But you don't want to fluctuate the temperature too much too quickly either. So it's a matter of testing and kind of double checking.
Right. Yeah, and it's not just temperature. You know, it's also there's basically a rate of dissolution, and you've got to give the sample enough time for everything to dissolve again too. Or Sarah, anything that I missed that you want to add?
No, I thought you covered that really well.
Mike Wallerack followed up that question with, how about freezing TSS?
Yeah, you know, TSS is kind of a goofy one too. You know, what I used to do when I first started, I would take TSS samples, and I'd put them in glass jars, and I would carry them to different presentations, and I'd say, this is what 100 milligrams a liter looks like, and I would shake it up, and you know, so people could get, you know, an idea of, you know, kind of a relative feel for my numbers. And what I noticed was I could do that with some samples, and other samples, if I let them sit for a week or two, I try and shake them up, and I just had like these clumpy flakes on the bottom, and you know, and I could get maybe 10–20% of the sediment back in the suspension, and the rest was just chunks floating around. And other samples, you know, I've had for 15 years, and I can go shake them up, and and they look fine. And the difference is the organic content in those samples. The samples that shake up and do really well are from the sewer, and it's all inorganic sediments, and the ones that don't shake up very well were from the Watershed, and there's a lot more organics in that stuff. So Mike, my concern would be if you freeze a sample, you might form those flocks on the bottom. I'm not sure. I mean, it would be another thing that pretty much I would stick to what the methods call for as far as preservation. But yeah, I mean, you could always try it and test it out, but I would be leery.
Great. Thanks, Pat. We're just about out of time, but
Okay.
I wanted to follow up with the final question of this seems like a really great service your organization has been doing for the region. With your upcoming retirements in your group, do you think PCA is gonna be able to keep doing this work?
Yes, I think so. We're trying to, Andy and I are trying to hand it off, and certainly Sarah will be a big part of this. But I mean, I'm easily replaced. Andy he had, it's too bad Andy's not here because he could add so much, but he's just got such a solid lab background that he will certainly be missed, and we'll be relying on Sarah more. So yeah, hopefully this will continue.
Well, I don't think that's true. I think you are greatly appreciated in the region. So, we really appreciate all the work both you and Andy have done in this group. That about concludes our webinar. So thank you, Pat, so much for your presentation. And everybody have a good day.
Great. Thanks for putting this on. I appreciate it.
Yeah.
Thank
you.